All right, section 4 in unit 4. This is 440. We're talking about indirect measurement. And we did that on our starter today. I don't know if you realize that. 4.3 is online. 4.4 is going to go online. 4.5 is already online, so you can watch it for tonight's homework. We kind of used indirect measurement today when we did our starter. When we were not in the scenario. She was not able to actually measure the height of the tree, but she used similar triangles to do that. Direct measurement is when you can directly measure any length. You can directly measure how far something is, how long something is. You can directly measure an angle. You get your protractor out, you could actually put the protractor on there and measure it. That's direct measurement. You could do that, where you can measure something exactly. You get your ruler out, you could get your tape measure out or whatever. That's called direct measurement. Indirect measurement is, well, basically when you can't. Because indirect means not direct. It's the in front, that little prefix in, it means it's not direct. So basically you cannot measure things. So what I would put down here is, you have to use similar figures. You have to use similar figures to get the measurement. You have to use similar triangles. You could use similar, quadrilaterals, pentagons, whatever. We are going to mostly go on triangles, is what we're going to mostly use. So here's an at-home example that you could actually try. It's called the mirror example. It does work. If I wanted to find out how tall that wall was, or how tall it is up to that top yellow poster, I could put a mirror on the floor right there, somewhere in the middle. And I could position myself where I could look in the mirror and see the top of that picture. That's kind of what you see right here. Is he wants to find out how tall the flagpole is. So he's got a mirror right here, and he's going to look at the mirror, and when he can see in the mirror the top of the flagpole, he would then have made two similar triangles. Triangles that would have angles in common. You'd have your right angles in common, you'd have your other angles in common, so you'd have similar triangles. And you could set up a proportion to solve this. You've got your height of the flagpole, you've got the bigger triangle. On this side, you could see this triangle coming down here, across here. This is your bigger triangle. You've got your smaller triangle. Coming here, he's the top leg. You've got your right angles. So you've got two similar triangles there. So we could set up a proportion to figure out how tall the flagpole is. What is a possible ratio I could use? Give me one possible ratio here. Give me the first fraction. Give me a fraction that will work. X over 6'3". Okay, 6'3". Should we go all inches or should we change it to decimal? 2 inches this time? Okay, what's 6 times 12? 72 plus 3 more? 75 inches. So let's put X over 75 inches. So what Yeska used was she used the long leg over the bottom leg in the big triangle. So if I'm going to stay consistent, then what do I need to use in my little triangle? It's got to be this side right here over this side right here. It's got to use my back leg over my bottom leg. So how much is 4 feet 2 inches? 48 is 4 feet. 50 inches. Okay, so I'm going to use 50 inches over what's 2 feet 1 inch? 25, because 2 feet is 24, plus 1 would be 25 inches. You see how I kind of made all nice numbers for us there? 25, 75, 50. So, hey, could we reduce 50 over 25? Yeah, we could. Divide them by 25. Divide these both by 25, and you do get a 2 over 1. Makes it a lot easier. Now I've just got 1 times x, which is 1x. and I've got 2 times 75, 150 inches. So 150 inches. If I take 150 and divide it by 12, because there are 12 inches in every foot. So what is 150? How many times is 12 going to 15? That would be 1, so that's 12. 30, how many times is 12 going to 30? 2 times, that'd be 24. Subtract, you get 6. Bring down the 0. How many times is 12 going to 60? 5 times. So 12.5 feet would be the height of the flagpole. I divided. Now you could have done this in your calculator. You could have done 150 divided by 12, and you're going to get 12.5 feet, 12.5 feet. But I did 12 into 15 once. Subtract, you get the 3 here. Bring down the 0. 12 into 30 2 times, because 12 times 2 is 24. Subtract, you get 6. Add a 0.0 here and bring down the 0. 12 goes into 65 times, so, and it goes in evenly. So the flagpole will be 12.5 feet tall. All right, let's look at another example. How are we doing here, okay? You need some more time on it? All right, second example. Using shadows. We kind of did that a little bit today, but this one looks a little different because this time he fits right inside here, and you hopefully can see 2 triangles here. Do you see 2 triangles? Do you see the big triangle? Everybody see the big one, right? So from here, down here, all the way over here to the end, and all the way up. That's your big triangle. Do you see the little triangle that he makes? Those are the 2 similar. Now, how do I know they're similar? Because they both have 90-degree angles. So I could put 90 degrees here and 90 degrees here. So they're both right angles, and they both have this angle in common because it's a common angle. It's in both triangles. So you have an AA postulate. You've definitely got similar triangles when you have AA postulate. So a 6-foot-tall person stands in the flagpole's shadow so that both shadows end at the same place. The flagpole's shadow is 48 feet and the person's shadow is 24 feet. How tall is the flagpole? So we've got 2 triangles, and we know the 2 triangles are similar because we know we've got the angle postulate. So give me a proportion that I could set up that would make this work here. Give me one ratio that would work. What is it? 1 to 2. Okay, how did you get that 1 to 2? Okay, so he's got well, you said 1 to 2, so I'm going to put the 24 on top then, right? So I'm going to put 24 on top. What does 24 represent? The shadow of the person, right? So the person's shadow, and what's the 48 represent? The flagpole shadow. So I did shadow over shadow. And then Christian reduced it for us, because 24 goes into 48 2 times, right? So it's a 1 to 2 ratio. So that would be shadow over shadow, the 24 over the 48. What about the second ratio here? Carefully now. We did small shadow over big shadow. I got to use small person over flagpole. So I got to do 6 over H. It's got to stay consistent. If you don't stay consistent, your answers are all over the place. So you did small one over big one, you got to do small one over big one here. So you're going to get 1 times H, which is just H, 6 times 2, which is 12 feet. So the flagpole in this case would be 12 feet tall. So that makes sense with similar triangles. You see how if the golfer would have been if the golfer would have made her shadow end at the same place as the other person's shadow, the tree shadow, that it would have been easier to do that as well. You could have just drawn 1 big triangle instead of 2. It will be online, so you'll have to do it. All right, let's go to the next example. Walter is standing next to a professional basketball player. The player's shadow is 2 feet 3 inches long. Walter is 6 feet 3 inches and his shadow is 2 feet long. How tall is the professional basketball player? Okay, so we've got our basketball player, right? And we know his shadow is 2 feet 3 inches long. And we don't know how tall he is. That's our text. We do know Walter, it's probably shorter, we're thinking, because his shadow is only 2 feet long. And he is 6 foot 3 inches. So you could essentially make your two triangles like we did on our golfer one today. So I need a good proportion that will allow me to solve for the height of the basketball player. I need a good proportion. What could I put over what? You want to do basketball player over basketball shadow? We could. It'll work. Or you could do basketball player over Walter. Basketball player over Walter. Okay, so basketball player over Walter, 6 feet 3 inches. Decimals or inches? Let's keep it inches. So 75 inches. So we did basketball player over Walter. We need to do basketball shadow over Walter shadow. So 2 feet 3 inches would be 27 inches over 24 inches. Can you reduce 27 over 24? Good by 3, yeah. Divided by 3, you'll get a 9 over 8. A little smaller. It's not a big deal smaller, but it's a little bit. Okay, so you got 8x and 75 times 9. Let's see what we get for that. 75 times 9, you get 675. And then you divide it by 8. So divided by 8 equals 84.375. Now if I take that amount and divide it by 12, I get 7.03125. So you're looking at about 7 feet. 7 feet, and let's see, what is 1/12? 0.02. So it's less than that. So it's just a little bit over 7 feet. So we'll put approximately. Approximately 7 feet. It's just a hair over 7 feet. It's 7 feet and half an inch, something like that. 7 feet and a half an inch. That's pretty close to what he would be. So he's taller than Walter. Walter's only 6'3". Basketball player is 7 feet. We knew he was taller because he had a longer shadow. Walter's shadow was shorter, so he had to be shorter. Similar triangle, indirect measurement. He did not directly measure this height. He used the similar triangles to measure. How did I get 75 inches here? Because Walter was 6'3". So that's 6 times 12 is 72 inches, plus 3 more would be 75 inches. So I changed them all into inches. And then at the end, I converted it back to feet. Okay, this is the last one. There is a little puzzle on the last page. Valerie walks 278 feet in a straight line from a point directly under the St. Louis Arch to the tip of the arch's shadow. So the arch, the sun is coming down here, and the arch, the shadow's way out here, and her shadow is, she walks to where her shadow and the arch's shadow are at the same spot. So she's making a triangle with the arch there. Valerie is 5 feet 8 inches tall, and her shadow is that of at that moment is 2 feet 6 inches tall. So she is 5'8". Her shadow is 2'6". And it says that she walked 278 feet to get to the end of that shadow. (278 feet to the tip of the arch's shadow. Then she positions herself so that her shadow, supposed to be, I probably should have put that in there, but she positions herself so that her shadow and the arch's shadow are the same. All right, so give me the proportion that will work, or a proportion that will work, because there's many that would actually work. You want to do x over Valerie. So Valerie, if we convert this, 5 times 12 is 60 plus 8 would be 68 inches. So we've got the arch's height over Valerie's height. So the last one has to be the arch's shadow over Valerie's shadow. So Valerie's shadow is 24 plus 6 is 30 inches. The arch's shadow is a big number. So let's see what that's going to be. 278 times 12. 3,336. That's how many inches the arch's shadow is. Could probably reduce it, but we would probably take a long time trying to figure out what to reduce it by. So let's just go ahead and do our cross multiplying. 30x, we'll do 3,336 times 68. You'll get 226, 848, and then you'll divide by 30. So x equals 7,561.6. Okay, that's how many inches. So we want to divide this by 12 to figure out how many feet it is. So divided by 12, you get 630 feet and probably like 1 inch. Pretty good. It's 0.133333. So pretty close to 630, and that's pretty accurate. I did actually look it up, and it does say 630 feet. So they are the same as 630. 630 feet. So using indirect measurement is when you're not directly measuring something, but you are using similar triangles to do so. So hopefully the similar triangles make sense, that you can match things up. When triangles are similar, the sides have to be proportional. All right, how are we doing on these? Good? Ready for the puzzle? Go ahead. Move to the puzzle here, see what you guys think. On your mark, get set, go. Raise your hand if you think you got it. Close. No, close. What? Nope. Really close, just one word. Let's get on with it. That's right. That was right. Okay, here's your puzzle. Number stumper, go. 52 weeks in a year is right.